Welcome to this video tutorial on how to complete the upright form tolerances. So what we're going to work on today is, let's see if we can zoom in here. Very nice. We're going to work on the upright, and we're going to talk about how to inspect for form variations. So we have cylindricity, straightness, and circularity, and those are really the three that we're going to focus on. And as I was in here making the blueprint, I said, we didn't talk about true position yet. We're getting to the end of the semester, and I'd be doing you a disservice if we didn't at least touch on true position. So I threw a true position tolerance in here as well. Now it's important to note that true position is actually both a location and an orientation callout, but we're only going to touch the basics here because this is a loaded topic. So basically we have our standard plane line alignment. It's very funny here. It's amazing. I look at my work after the fact and I realize, geez, I just missed details. This is supposed to be datum A, this is supposed to be datum B, and this is supposed to be datum C. So 1 out of 3 ain't bad, I guess. And as we go through the video, you'll find that, yeah, that top plane is the primary datum, and this is the secondary datum. So I apologize for that. That'll be corrected by the time you see the print. All right, so all we need is some basic dimensions to locate our hole, 2-inch 0.25 and 7.25. Notice that I know they're basic dimensions because they have the rectangle around them, and that rectangle means that they refer to a feature control frame for their tolerance, and those will be held to a locational tolerance with a round tolerance zone. That's what this true position means here, of 3 thousandths. And the size of our hole is only going to be 500 thousandths plus or minus 10, so it's a really wide open tolerance. You might say, geez, this seems even easier than some of the parts that we've been doing. We can just touch 1, 2, 3 points on this diameter and call it good, right? Well, no. We actually can't because of these form tolerances here. Now, I also want to point out that a lot of times you would see only one of these tolerances, maybe two. Maybe you would see true position coupled with cylindricity. Maybe you would see true position coupled with circularity, but you often wouldn't find circularity, straightness, and cylindricity all on the same feature. In fact, there's quite a bit of overlap there where, as you'll see, cylindricity is really like straightness and circularity all wrapped into one callout. So we're going to do all 4 of these in this tutorial, mostly so you don't have to write a whole bunch of separate programs, but keep in mind you wouldn't often see them all coupled on the same callout on a drawing. So anyway, let's get right into it. So we'll pop on over to Calypso here, and I'm going to open up the work in progress file that I have from the last video when we learned how to orient this part on the machine. And I'll go to measurement plan simulation, and the only thing I've done so far is place this model on the machine. Now, one thing I didn't look at when I was placing this model on the machine, does this line up with the blueprint? And looking at the blueprint, I see that we're in the wrong orientation. So we really want to have the counter bore up. We want to have what we're inspecting, this 1/2 inch diameter hole on the right side, and these tapped holes over here want to be facing the front. Okay, and if we look at that, we have that mostly correct. We do at least have the counter bore up. We can see that over here. The counter bore is up. However, these tapped holes on the left side, they should be on the front. So we really want to rotate this model. Now, I spent some time trying to find the easiest way of doing this before I started this video. And the long and short of it is, there's no real clean, easy way of doing this. I tried correcting it by just creating the base alignment, doing a plane, line, and point alignment. When I did that, it wanted to make this line here the minus y axis. So I forced it to be the plus x. I said, I'll show you. I'll rotate this using the base alignment. And what happened is it rotated the base alignment coordinate system on the machine so that the x-axis was the y and the y was the x. And I don't think that's what we want to do with that. So I also tried rotating these components individually, and the problem with that was, well, you can rotate this one individually easy enough. However, there are no great tools for rotating this one and this one unless you set a base alignment in the center of the part, and that's more effort than it's worth as well. I tried coming up here and using CAD and modification and CAD model transformation and moving this entire CAD model as one piece. And let's do that right now just for ha-has. This one seems like it would work. This is really the CAD modification tool for assemblies, is what I would call it if I were making the software, right? The problem is that rotates about the base alignment, and the base alignment is way up here. That's not what we want, right? So let's move that back to where it was so we don't accidentally hose ourselves here. So what is the happy medium here? Well, in my opinion, the happy medium is I would not move this model over to here in Calypso. Can you do it? Yeah, of course you can. I just made a whole video on how you can. Is it wise to do that? Is that the easiest way? Probably not. So if we have this in Mastercam or SolidWorks, we could simply open up that file and just rotate the model locally. We would already have the delta X, delta Y, and delta Z from the origin in there. If you follow the videos from last week, they show you how to do that. And then we could just locally rotate this part, save it out again, re-import it, and we're done. Here, we don't have that as an easy option because I did all of this locally in Calypso. So first thing I want to bring your attention to is all of these are individual models as of right now. And in one of the previous videos, I said I think I said anyway, I can't think of the application where you would want to combine CAD features because it causes problems down the road. Well, I'm going to go back on those words and say right now, I'm doing it. I just combined the CAD features, and notice that in our hierarchy now, we only have one CAD feature there. Notice also that it looks like it combined the table of the machine, if I'm not mistaken. It looks like it grabbed the entire table model of the machine and called that the CAD model as well. So that is something that I noticed as I made the video. If you have that table model on, it will also combine that as part of the CAD model, which you would think is not that big of a deal. But then when you go to create a clearance plane, it does create some issues. So I combined this CAD file here. This is now all one CAD file. And what I like about that, now I can use these CAD tools down here. This is Modify CAD Model, or you can get them from up here too, right? Modify CAD Entities is the same thing as Modify CAD Model. So now I can use this instead of modification. And what I like about Modify CAD Entities is that we can do a transformation and we can grab our one model now and we can rotate this 90 degrees and we can do this locally. So if we look at our preview here, it looks like it's going to rotate everything, including the table, about the base alignment, which is, the base alignment's way up here. That's not what we want. But if we use the center button, that gives us what we want. So the availability of this center checkbox, it's only available on the individual model level, and that's why we had to combine all the CAD models. So anyway, let's hit apply here, and now everybody's happy. We have corrected the rotation of our model, and now we can move on with our lives. We are now in the same orientation as the blueprint. Can you write the program in a different orientation than what the blueprint says? Yeah, absolutely, you can. But oftentimes it ends up getting more complex. You have to do some mental gymnastics to try to figure out what's what. Someone might say, hey, you can just either rotate this PDF 90 degrees. You could just right click and say rotate clockwise. Yeah, you certainly could do that. That is a viable solution to this problem. You could also just print the blueprint out and hold it in the same orientation. Yeah, that's another solution. But also, I wanted to show you some of these CAD tools and how they integrate. So I digress. Our primary datum is going to be the top surface. Secondary is the front line. Tertiary is the left edge. All right, let's turn off our plate model here. You notice that plate model is still here because I had that plate model on at the time I combined the entities. Yeah, the software can be a little bit hokey. So let's create our base alignment. And we'll just accept the defaults and say, okay. We'll hit the pull-up, say define select geometry. We'll grab the plane on the top. We'll grab a line on the front. Now, even as you're watching this, you're probably thinking, hey, we have to make sure we jump up and over this fixture. Yes, absolutely, we do. And that is part of the reason why we created this fixture model to begin with, is just to help at least my feeble little mind remember that there's some stuff there I got to watch out for. right? So other people may be able to keep all that information in their heads. I am not one of those people, so I need to have the CAD model, and I think probably the majority of the population is the same way. That CAD model is really going to help you. Just, remember all of those odds and ends when you're on attention to detail overload. It's helpful to have that CAD model to help you remember things like that. So let's go into our clearance plane and say clearance plane from model and OK. And up until now, this has been fine. But now we have the entire table in there. So that's not going to work for us. We'll say OK to that. And how do we get around this? Well, we certainly could create a clearance plane manually, but that's not what we want to do. Let's go modify our CAD models. And now we can't edit the body and just click on this and delete it because it's all one surface. But we can come up here to the edit menu, and now we can select one surface individually, and we can hold control and select other surfaces as well. So we could delete them one at a time, or we can mass delete them by control selecting and just say delete feature. Right, so now we get the best of both worlds. This technically is all one CAD model, and we got rid of that base plate that we put in there by accident by having this turned on, right? Keep in mind it will capture the base plate as a CAD model if you have it on. When you come up here and go modification, CAD modification, and combine. So let's go back to clearance plane, and we have this massive clearance plane. Let's say clearance plane from model again and OK, and you see that is a much more reasonable clearance plane. Do we want to update our clearance plane for the features? No, we do not. All right, so our base alignment is all set here. Well, we want to come back to our features and make sure that our points are not going to hit our CAD model, right? Very easy to forget this, as I was just saying. Right, so we come into strategy. I don't want a polyline for this, so I'll delete it, and then I'll touch, let's see, what do I want to do here? I'll go 1, 2, 3 points on that plane and say OK, and OK. And then on the line on the front, we're going to have to avoid this fixture here. So we'll go strategy and get rid of this auto path. That's not going to be able to jump over anything. We'll create a point, and then let's copy our clearance data, and let's just paste that in there. And then let's create another point on the other side. Right, so now it's going to go to its clearance plane, come down, touch, back to the clearance plane, over, come down, and touch. All right, and I think we are good for those alignment features. We can grab all three of those and form a group here. Can we? Oh, don't tell me I'm frozen here. All right, technical difficulties. I'll be back as soon as I unfreeze this. Yeah, I don't know what that was about, but we're back now. So we'll highlight that, form group, and then we'll right click on it and we'll rename it, and we'll call that align just to keep everything straight there. So looking at our blueprint, we are now aligned to A, B, C. Again, this is A, this is B, and this is C. That's our primary, secondary, tertiary alignment, our datums respectively. Okay, so what do we do? Well, let's do these bottom to top. We are going to do this roundness callout first. So roundness is a 2D callout. We want to do this with a circle. So you would think you can come up here to define select geometry and just click on that and it would grab a circle. If you do that, it'll grab a cylinder. So we actually want to grab a circle on a cylinder, and we'll just click directly there. And I think we can get this circularity callout. We can also get this diameter 500 thousandths through. Well, the diameter 500 thousandths through is right here. That's our D. That's a direct characteristic is what they would call that. And that is actually going to be plus or minus 10. Right? So already we're checking that this is round within 20, but the blueprint says that this has to be even rounder than 20 thousandths. So let's jump over to characteristics here. You can see our circle diameter right there. And you might notice that, hey, this circle diameter is not, it's not green. And also notice that our circle over here is not green. Why is that not giving us any information? Well, we haven't run it yet, right? So we know what we're going to do on this circle, but we haven't actually collected the point cloud to be able to output that. So this is just the circle diameter. This makes sure we're round within 20 thousandths, but the blueprint says we have to be round within even more than that. So this is an important thing to note when you have GD&T callouts that have to do with form. you only apply the GD&T callout if they constrain the model more than the feature of size tolerance. So this is already controlling it to plus or minus 20 here, which granted is massive. But if this was 500 thousandths plus or minus 1, well, the total tolerance there is 2 thousandths. That would be tighter than this form callout of 3,000 circularity. So this would be unnecessary. This would actually be double dimensioning and would be confusing. So you only apply GD&T form callouts when they constrain the model further than the other dimensions. All right, so this is going to be a roundness value of 3 thousandths. Our feature is going to be circle 1. We say OK, and this is so cool. We can come here to PyWeb reporting plot view, and we can say plot. And right now, this is going to give us an error because two things. Number one, we have not created a point cloud yet. And number two, we only have 3 points on this feature by default, or at least the way that I set up my defaults, I only have 3. So we'll come in here to strategy, and you can see circle path. And if we double click on that, notice I have number of points is 3, and I have single points checked on. So the first thing I'm going to do is uncheck that. And I'm going to switch from number of points to step width. And my default for step width is 5 thousandths. Right, so my default is 5 thousandths. Well, I'm going to come up here and click calculate. Oh, don't tell me we're frozen again. All right, technical difficulties. Be back momentarily. All right, and we're back. So for step width, we'll set that to 5 thousandths. And if you hit calculate, that actually will modify these values based on your speed. It will tell you what your optimum step width is. When we get to the cylinder, I believe you hit calculate and you have some options where you can do it for size, location, or orientation, and that'll further modify these values. For right now, let's set our, I think I did this in the wrong order before, and that's what caused it to hang up. Let's set our speed to 0.5. That's how quickly I'd like to scan. And then let's hit calculate. Let's try 0.005 and 0.5. Very funny. Okay, so it doesn't want to let me do anything other than a step width of 2 thousandths at a speed of 0.1575, and that'll give us 800 points, I guess. I'll let the baby have its way for now. We'll say OK here and OK. And we'll come back in. It looks like all of the alignment features have already been done. We already have data for all of those. So let's come and highlight the circle, and we'll say run. And we're going to run the current selection only. And we're not even going to clear the existing results. So we'll be going on current alignment. All right, we'll hit start, and we'll see that this will only measure that circle. And you notice it's doing a scan path rather than individual points here. Okay, so now we've acquired all the information we need from the Features tab, but we haven't done anything in the Characteristics tab yet. We can just go run and say All Characteristics. We won't clear the existing results, and we should see no motion over here because the machine really wouldn't move. It would simply dump that point cloud into our characteristics list. Now, it's almost like a tease that pops up. It shows us our dimension report, or it looks like it's going to, and then it doesn't actually show it. So let's hit View and Multiple Report, and that will bring that information back. So you can see that the diameter on the actual model is 5025, but our nominal value is 500 thousandths. We got plus or minus 10, and we're using up 2.5 thousandths of that tolerance. Looks like our roundness is coming in at 1 thou and 5 tenths. Our nominal value is 0, high limit is 3, so we're right in the middle of our tolerance there. Now I'm going to come back to roundness value, and I'm going to hit the graph now that we have actually scanned our model, and I'm going to say plot, and notice that this has dispersion on. And I know it has dispersion because this model is theoretically perfect. It was made in a CAD system. So that circle should actually be a circle, but this is showing us a lot of variation here. So this looks actually somewhat random, but it really looks more calculated by a computer than you'll see in real life. Oftentimes you'll see like an egg shape where the part was squeezed in a vise, you ream a nice hole in it, you let it go, and now it kind of morphs back to this weird egg shape. Other times you'll see just scuffs from tool marks where maybe you're coming in there with a reamer, you stop the reamer at the bottom, and then pull it out, and you pick up a chip, so you end up with a scuff mark on all of the 6 flutes. So you might see stuff like that there. So why is this looking so calculated, and why is that showing us some deviations here? Well, that's because I came to Extras, Settings, Miscellaneous. I'm sorry, I came to Extras, Settings, and come on, Extras, Settings, and Measurement. And I came down here to Simulation, and I turned my dispersion on. If your dispersion is off, let's turn it off for a second and hit OK. Well, first of all, if you turn it off and then you come back in and look at exactly the same feature, you will get exactly the same results because the results are being pulled from the last point cloud that you executed, right? So if we want to update that, we have to come to the Features tab, highlight the circle, say Run. We do have to clear our existing results, but we're only going to check our current selection, and we'll say Start. And this isn't even going to do the alignment or anything because we're in current alignment. It's just going to inspect that one circle. Now when we come over to characteristics, we can double click on roundness, click on that, click on plot, and this is redumping those values. And look, we have a perfect circle. We make perfect parts. So if you ever want to make your part look perfect, I guess, run it in simulation with dispersion off and it will look good. Now, for the sake of this video, it doesn't make any sense to be talking about form variations and to have dispersion off because we won't see anything on our graphs, right? So let's go Extras, Settings, Measurement, come down to the Simulation tab, turn dispersion on, and set the values as shown here. So our from is going to be 0.0005, our to is going to be 0.0020, x is going to be 0.001, y is going to be 0.002, and z is going to be 0.003, and then say apply and OK. All right, so one thing down, we got our two things. We have our diameter 500 thousandths. Note that through is a reference, so we're not even inspecting that. It's going to be 500 thousandths plus or minus 10. We got that. And this is round within 3. Now let's talk about cylindricity. So cylindricity is needs to be within 3 thousandths on this part. Well, we actually can't even do cylindricity with a circle. So we have to come back, and you would think you'd click Define Select Geometry, but keep in mind this only will extract features that have not already been extracted. And if features have already been extracted, it will simply highlight them in your features list, in this case, circle. So right now, this is not going to work for us. And you would think you can come in here and select a cylinder, but there's no option. So what do? Well, we want to actually hit Extract Features, and this will allow us to do duplicates, whereas this will not allow us to do duplicates. So this is Calypso trying to be too smart for its own good, and here is the workaround for that. So we'll click on that, and we'll click here, and notice that that gives us the cylinder. So if we double-click on the cylinder, notice that the default strategy, at least that I have, is circle path 2 sections. So that would be generated from here, 2 circle auto paths. Well, that's actually technically enough information for us to do cylindricity, so we'll leave it for now. But let's double click on it and let's just modify our values. So for our speed, we're going to set that to 0.5, and then for our step width, we'll set that to 0.005. 2 decimal points there, sorry about that. Notice that single points is checked on by default in my system, so I'll check it off. Right. It's also very funny when you check single points on, look at all the individual points that it would have to go beep, 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 beep. That's what all the X's are about. So that would take a very, very long time if we didn't have a scanning head. Here's where I was expecting to say calculate, and there we go. This is what I was looking for in the 2D circle. Apparently it does not exist for 2D circles, but it does for cylinders. So we can calculate this for location, size, or form. So let's go for form. So we have our standard default values in there. Notice that the number of points per section is 315. When we say OK to that, notice that it slows it down all the way to a step width of 2 thousandths and a speed of 0.1575. So I guess that's where it wants to be. And that brings us to 800 points. All right, now scanning at a speed of 0.1575 is quite slow. And when we're adding in 2 sections now, man, oh man, is that going to increase the cycle time for our program. But hey, that's what you have to do if somebody really wants something to be cylindrical within 3 thousandths. Now, technically, the absolute minimum number of points that you could use to output cylindricity would be 6, right? 1, 2, 3 individual points at the top, 1, 2, 3 individual points at the bottom, and that would look like a perfect cylinder. So I guess 7 would be the minimum number of points to see any sort of deviation on that. And even at that, you'd only see roundness either at the top or the bottom. So we need to have all these points to be able to output our cylindricity with any sort of meaningful information. All right, so we say OK here, and just for ha-has, we did already output the diameter, and the diameter will end up looking the same whether we do it off the circle or the cylinder, at least when we're doing this in simulation. But when we do this in real life, if you output the diameter of the cylinder versus the circle, it should give you 2 different answers. And the reason is the cylinder has a lot more information. So we're going to add both to our dimension report. So that way when we run this in class, we will actually see that difference. Now this hasn't been run yet, so we'll highlight the cylinder. From the features menu, we'll run current selection. We will clear the existing results, and then we'll hit start. And that is only going to run those 2 circles right there, circle paths rather. And then we'll come over to characteristics. We do see our cylinder diameter here, but if we want to output our cylindricity, that's going to be in the form and location pull down, and we'll come down to cylindricity. And cylindricity is really like roundness on steroids. Roundness is 2-dimensional, cylindricity is 3-dimensional. So let's come into cylindricity. We'll click on our cylinder and say OK. We'll set our tolerance value to 3 thousandths, and then we'll do our form plot, and we'll say plot. And again, if you hadn't already run this, it would not give you any usable information here. And there you go. You can see whether we fit into the geometric perfect cylinder. You can also see the difference between the 2D plot and the 3D. When you output circularity, it shows you the top view of this. So it's as if you're standing right here looking straight down onto the plot. Here, when you want to see it 3-dimensionally, you need to look at it isometrically. Okay, so that's that. We see all the variation here because of dispersion. You will likely see very different shapes. These do look like they're calculated by a computer. A computer has a hard time simulating the actual randomness that we would see in the real world. So this is simulated randomness. In the real world, you might see egg shapes, you might see taper, or something like that. So cylindricity is comparing the actual measured value to the theoretically perfect cylinder. All right. So now we've done circularity, we've done cylindricity, and we've done this diameter. We actually did this diameter twice. We looked at it once for the circle, once for the cylinder. That will show us different values in the real world. So let's talk about straightness. So straightness within 3 thousandths. So you would think you could just grab that cylinder that we just grabbed, and we could come over here to form and location and go to straightness. We could double click on that, grab the cylinder 1. We could also grab a line, by the way. This is the initial line that we created with our alignment. We'll set our tolerance to 3 thousandths, and we'll come and plot this, and we'll say plot. And this line is perfectly straight. We have 0 form deviation error, and it's like, how is that possible? How can we have 0 form deviation error? Well, the definition of a line, the mathematical definition of a line is the distance in between 2 points, the straightest path in between 2 points. Well, here we actually only have 2 points for the cylinder if we're looking at it in terms of straightness. And you might say, but Tom, we have like many points. We have 1,600 points. How is that possible? Well, we do have, well, it's 798 points, top and bottom, I guess. So it's whatever that would be, 1596 or something like that. But when we output straightness, that is taking the centroid of this top circle path and the centroid of the bottom circle path and connecting them with a line and telling us whether that line varies. The long and short of it is we don't have enough circle paths to do this. The minimum number of circle paths to get meaningful information out of straightness would be 3. So you see, all we have to do is edit our strategy as we're doing and then increase our number of sections to 3. Now, is 3 really going to give you accurate results? It's not really enough to be able to do that. This says it has results, but it has not updated based on the new strategy that we're using. So we'll say run. We will clear the results. We'll do current selection only and say start. And now we'll see that we do 3 circle paths, and now we'll see something quite different when we look at our straightness callout. All right, so we'll come over to characteristics, we'll come into straightness, we'll plot it. We haven't changed anything other than the number of circle paths that we're measuring. And now you can see, hey, we do not have a perfectly straight cylinder anymore. So you see, cylindricity is really looking at circularity and straightness all put together, wrapped into one callout. Well, sometimes you only want to know if the thing is straight. You don't really care if it's round. Other times you want to make sure things are round. You don't really care if they're straight because the features maybe are not that deep. But cylindricity is an extremely expensive callout to put on a drawing. Sometimes straightness or circularity would work better for the application that you want. Now, this really is only giving us 3 data points. That is very prone to statistical outliers. So if we really want to do this right, we would come over here to our cylinder, we would edit our strategy, and I would say at a minimum, if this really matters, we would want to have at least 5 sections. Right now, Calypso offers a, they call it a cookbook. It's a measurement cookbook. Let's go back and update this again. We'll go run and start. So they offer a measurement cookbook, and basically it gives you, this is funny, they call them recipes for how you need to measure your part based on whatever call out you have on your drawing. And the recipe that they would use when straightness is required would be at least 5 circle sections on a cylinder. So let's come over to our characteristics list. Let's look at our straightness again. We'll go to our form plot and say plot. All right, now you can see some very different results here. Again, this is all computer simulated errors using dispersion. We're going to see something that is much more meaningful when we run these on the real part in the real world. It'll tell us more about what's really happening with the manufacturing process. So far we have done roundness, straightness, cylindricity, and we did the diameter twice. Now let's talk about true position. This almost should be its own video, but I'm just going to sneak this in here real quick. Let's do true position of, geez, well, that's an interesting question. Do we do true position of the circle, the 2-dimensional circle, or do we do true position of the cylinder itself? And to be honest with you, I don't have a great answer for that question, but I do know that you will get different answers if you do it 2-dimensionally using the circle versus 3-dimensionally using the cylinder. And I also know that true position technically is 4 things wrapped together. It's X position, it's Y position, it's tilt about the X-axis, and then tilt about the Y-axis, right? So it's 4 things added together. So this is really a 3-dimensional callout. So if we do it with the circle only, we're not seeing the X tilt and the Y tilt. Now, with that said, I have seen many inspectors and CMM programmers inspect for true position 2-dimensionally. It kind of makes you cringe when you see it, but obviously they must know something that I don't know. So anyway, we will output our true position to the, let's see, which one do we want to do? Let's output our true position to the cylinder. Let's do that. Let's say position. So this actually calls it position, not true position. So we'll go position 1, and for our feature, let's grab cylinder 1. And notice that that picks up our X and our Y for us, and our X is 2'025 and our Y is 725. Well, where did those come from? Well, they came from our base alignment, datums A, B, and C respectively. So it pulled our basic dimension, 2'025, and our basic dimension, 725, and these do not influence the tolerance at all. They just say where the center of this should be. The actual tolerance here is a diameter of 3 thousandths, meaning we establish the theoretical center point, or central axis, if we want to think about it 3-dimensionally. And then this expands that center point, if we're talking 2-dimensionally, or central axis, if we're talking 3-dimensionally, by a diameter of 3 thousandths, meaning 1.5 thousandths in any direction. So we do have diametral. We could do polar, which really means radial. We could do rectangle XY, only X, only Y. So by default, true position is a round tolerance zone. This drop down here will let you change it to a rectangular tolerance zone, but honestly, we do not have rectangular tolerance zones. So this is going to set it to a diametral tolerance zone of 3 thousandths. Our nominal X and Y are good. This grabbed the primary, the base alignment for our primary datum, which is exactly what we want in this case. All right. So we can either calculate it from the center line, which is just as far as we measured, right? We measured circle paths, top. Well, we did 5. We did top, bottom, and then 3 in between. We can also project this tolerance further out to the extents of the part if we want, or even further if the print requires it. I'm going to select as the recorded center line here. And then we'll simply say OK. And then let's double click on this. Whoop, I'm sorry. Let's come to View and Multiple Report. And let's take a look at what that position call out actually gave us. So ultimately, that wraps all of that up into one number, and it simply tells us whether we're in tolerance or if we're out of tolerance. Now, I know that there's a setting in Calypso somewhere, and I don't know where it is off the top of my head, but we can break that out into X position and Y position on our report here as well, and that can be extremely helpful for diagnosing setup issues. I'll have to cover that in a later video. But for right now, we just know that we're out in some capacity. We're at 4, 6. Okay. I just want to show you the difference in between true position versus X coordinates and Y coordinates. So right now, our base alignment is exactly where it needs to be based on this call out. And we did just output this tolerance here, true position. It's actually pretty quick and painless on a CMM, but man, oh man, try to check true position in the real world. It's quite a bit of setup, and you have to use a surface plate and a height gauge and an indicator and all this stuff. This was relatively quick and painless comparatively, right? So that one true position callout included both basic dimensions. It included all of this. This is regardless of feature size because there's no MMC or LMC modifier here, but true position also has the ability of doing MMC and LMC modifiers. This is particularly helpful on CMMs where it does the math for you. We didn't have to worry about that here. Right? So all of this, and this are all wrapped up in that one true position callout. Well, just for ha-has, let's come back here and output this as a regular X dimension and Y dimension and just see if our part falls in tolerance. Well, if we do just a regular X dimension and Y dimension, if we don't understand what these rectangles mean, right? Well, that's 2 inch 025 is a 3-place decimal, right? Plus or minus 5, plus or minus 5. Again, this is wrong. I'm just telling you why it's wrong. If we do that, if we come up here and we go to size, standards, and X, and let's go grab our same cylinder that we output. And we leave that at the nominal value that it's at, but we give it plus or minus 5. And then we'll go size and standards and Y, and we'll leave that at the standard. Whoops. I'm wondering why it doesn't have the nominal. It's because I didn't grab the cylinder. There we go. We'll leave that at the standard nominal of 725. And we'll set this to plus or minus 5 thousandths. Well, first of all, there's a problem because we have way more tolerance here. Look at the X and the Y values. They're both green, whereas position is red. How is this possible? Well, let's come up here to View and Multiple Report, and I think this will tell the story. All right, so here our position has a center line that has been offset by 3 thousandths diametrically, which is really 1.5 thou per side. So this gives us a round tolerance zone with a diameter of 3 thousandths. This X value is taking the center line and it's offsetting it 5 thousandths in the negative direction and 5 thousandths in the positive direction. So we actually have a line that is 10 thousandths wide, top and bottom, let's say. And then our Y value is also taking our center line, 725, and it's offsetting it plus and minus 5 thousandths. So that is our left and right line that forms our rectangular tolerance zone that is 10 thousandths in any direction. So here we have round tolerance zone with a diameter of 3 thousandths, and here we have a rectangular tolerance zone that's 10 thousandths wide by 10 thousandths tall. So two completely different callouts. It's so important how you interpret what this blueprint says right here, and that is the fundamental difference between true position as opposed to just rectangular coordinates. All right, so one last thing, let's run all of these. Let's get rid of some of these extra PyWeb reports that we have open here, and let's run all of our characteristics. We're going to run all of our characteristics. We will clear the existing results. We will run with our manual alignment, or I'm sorry, our named alignment here. All right, so there are scan path for the circle, and now we're starting the scan paths for the cylinder. All right, and once we have all of that, our dimension report should pop up, and this is what I want to see on your dimension report that you hand in. We should have circle 1 diameter, should be nominal 500, plus or minus 10, just like the print says. Roundness 1 is going to point to that circle. It's going to have a nominal value of 0. Tolerance is 3 thousandths. I also want to see the diameter of the cylinder. Now I understand the cylinder and the circle really say the same thing, but you'll see when you run this in lab that they do not say the same thing because the cylinder has way more information than the circle does, right? Cylinder's nominal is going to be 500 thousandths plus or minus 10. Cylindricity is going to have a nominal of 0 with a tolerance of 3 thousandths. It's going to be pointing to that same cylinder. We're also going to output straightness of that cylinder. Nominal is 0. Tolerance is 3 thousandths. We are going to output the position of that cylinder. Nominal 0. Tolerance is 3 thousandths. For your nominal values that are the basic dimensions, they should come from the base alignment, which is going to give you 2-inch 025 in the X and 725 in the Y. Even though the print doesn't say this, I want you to see this in the real world. I want you to see this on the real part. I'd also like you to add the X value with a nominal of 2-inch 025 plus or minus 5. This is simulating as if the programmer did not understand what true position means and they output it with the wrong callout. And I'll do the same thing in the y-axis. The nominal will be 725 plus 5 thousandths minus 5 thousandths. Something else I'd like you to include in your submission. You'll submit as normal, but you'll also add 3 different JPEG images, and I want those to be outside of any zipped folders so that way it's easy for me to grade. I'd like you to include your roundness plot as a JPEG image. So you'll take a snip of this, you'll say new, you'll grab this, and you'll save this as roundness, or circularity actually. That's what the ASME Y14.5 would call that, right? So circularity, we'll X out of that, close and close, and then we'll come down to cylindricity and do the same thing, and then we'll come down to straightness and do the same thing. So I'd like you to include those 3 JPEGs with your submission as well. So thank you for watching, and I'll see you at the next video.